Greetings and salutations to you Algebra 1 students. I know, I usually say what's going on, but I mean, that's just kind of my thing. If you are there and you can hear me and you have pulled the macapia out of your eye, say good morning. Even though technically it's 10:32, you can't hear you good. I can't hear you good. Is everyone having trouble hearing? Hello? Is everyone having trouble hearing? It's very scratchy. That really stinks. Hello, can you hear me? Is the audio coming through all right? Oh, this is going to be one of those days. I'm sorry. I'm going to apologize off the bat. I'm sorry if the audio is not coming through all right. Do your best to hang in there with class. I'm going to record this as best as I can, and then hopefully, you'll be able to at least hear in the archive. But I want you guys to attend class because I think the class is probably one of the most important parts of it. But anyway, should I log out and log back in? You want me to try that? Alright, I'm going to log out and log back in. Let me know if it works better. Give me a second. Check, check. 1, 2, 1, 2. How's the mic coming through? Is it better? What up, dude? Hey, come on, have a seat. Is it a lot better? Awesome, awesome. Oh, I hate that. Alright. I'm going to try the video now. Hold the chair. I'm going to try the video now. Hopefully that works. I'm wondering if having the video up is what's causing the audio to go bad. If that's the case, then I got a problem. I'll do my best. Alright, I'm doing the video at the lowest possible quality I can get. Can you still read this? Actually, no one can read that. Hold on. That sucks. Can't see that. Can you read that? It's terrible. It looks terrible to me. I got all this technology in my room and none of it works. I'm going to up the video quality because I can't stand it. Does this work better? Can you see this? Alright, can you hear my voice? Can you hear my voice alright? Am I all staticky? Okay, so you can hear my voice and you can see clear enough. Because I'll be honest with you, the reason why I'm a little blurry is because I have to bring down the video quality in order to make sure that you guys can see and hear at the same time. Which is kind of lame, because I would have hoped that you guys can be able to see and hear me at the same time. Your echo. I echo. Well, look. I'll be honest with you. You can't see me. Why can't you see me? Can everyone else see? Okay. Then what you're going to have to do is you might need to log out and log back in because I don't know how to fix that.
There might be some kids who are downstairs watching your class. I don't know.
Are there anyone who's here on campus and watching the class? Actually, you know what? I'm gonna let you guys hang out. All right. So let's get this party started.
Which functions is this?
You can't see me and you echo. To be honest with you, log out, log back in. That's the best thing I can do for you because if other people can see me and hear me, then that might be more of your computer thing and not so much of a my computer thing. Not to be harsh. I don't mean to be harsh like that. Was that harsh?
No. Makes sense.
All right. Okay. All right, so we're on function 7. We're going to be covering more on graphs. And I'm looking at function 7, handout 1. This is what the graph looks like. And we actually covered part of this. I think that, was it you, Tejas, who had your skateboard with you?
No.
No, it was somebody else. Somebody else brought their skateboard in and we started playing on the skateboard and all that good stuff. Dude, do you ever bring any of your
No,
stuff?
I had it with me today, and
No, I don't. I'm sure it's in that pile up there. You can feel free to go look through it if you want. All right. So check this out. Here's what I'm going to do. We covered the first 3 pages, and we started talking. The last time we talked, I think, was on Friday. And the last time we talked, I pushed this kid around on a skateboard. What I want to do now is I'm going to cover for you this idea of translating between a distance time graph and a velocity time graph. And I think I'm going to start an easier version for you, if that's all right. All right? I'm going to have a straight line that goes like this, okay? So take notes because this isn't technically in your class, all right? What the velocity time graph, if this is the distance time graph, tell me what this story looks like. If I give you this distance time graph, can you tell me what the scenario would be? Type it out in the chat bar. Tejas, you can tell me because Tejas is sitting right here. You logged out, I logged out, but there's still an echo. But can you see me now, Kiana? Okay, at least you can see, and there might be an echo, but you know what? I really can't fix that at this point. All right.
in a fast amount of time, he went a further distance.
In what?
In a fast amount of time, he went a further distance.
All right. So as time, Tejas is saying, as time goes by, the distance grows, right? So he's moving away from whatever he started. If this was his house, then he's moving away from home, right? He's walking away from home, right? I have a question for you. Is he speeding up? Is he slowing down? Is he moving with a constant velocity?
It's moving quickly because it's going upwards, so it's inclining.
All right, I want everyone to answer. Because, by the way, Tejas isn't correct necessarily. My question is he speeding up, is he slowing down, or is he moving with a constant speed? Sarah says constant velocity. What do you think, Tejas? What does everyone else think? Everyone says constant. Yeah, because the slope of the distance time graph is describing how fast you're moving, and this slope is the same. This slope right here is the same as that slope right here is the same as that slope right there. It's the same. It's a constant speed. So on my velocity time graph, by the way, is this slope positive or negative?
Positive.
It's positive because it's going up. As you go further this way, it goes higher. The slope is positive. Also, is this slope big or small? Is it big, or is it small, or is it medium?
Medium.
I would say it's medium. Okay. So that means when I graph a velocity time graph, that thing translates to a constant velocity, but there is a velocity. It is not moving at 0. Okay? And it's a medium height. So it's constantly going like this. This velocity time graph is the same exact thing as this distance time graph. It's describing the same person, the same motion. They look different because I'm describing something different. I'm describing how the velocity is as opposed to how the distance is. Does that make sense to you? But they are totally related to each other. Now, if I continue this graph and at some point I go like this,
That would mean he started going at a constant rate, right?
all right? No. All right, Tejas, say that again. What does this part of the motion describe?
Constant.
A constant what? He's constantly doing what?
Moving at a certain speed.
He's constantly moving at a certain speed. I disagree with you. He is constantly moving at a certain speed over here.
Uh-huh.
Over here, I guess technically yes. He's constantly moving at a certain speed. That certain speed happens to be 0.
0.
You're not moving at all.
He stopped.
He got shot. He is dead on the ground. Boom. What is his velocity?
It's down there.
What is his velocity, though?
0.
It's 0. So it bumps down to 0. That graph would look like that. It would go moving at a constant velocity, moving at a constant velocity, getting further and further away from the home, and then boom, you get shot, and then boom, your velocity is 0. Does that make sense?
Yeah.
All right. Now, I'm going to do something a little advanced for you, okay? Let me erase this. Now I'm going to do something funky. I'm going to do this one, okay? Can you tell me, because I told you that when we take the distance time graph, if we want to figure out what the velocity time graph, we look at the slope. But what is the slope of this curve? This right here is called a parabola. It's actually half of a parabola. Actual parabola looks something like that. Okay? So we got half of a parabola. What is the slope of this curve? And your answer is, what are you talking about? How do I find the slope of a curvy line? Right? Is that what you're thinking in your head? There is no slope. Actually, there is a kind of slope that's related to it. And I'll tell you what. I have this dirty rubbery thing right off the ground. It basically holds wires and everything. Just think of it as a straight line. Okay? Remember I told you that there's this idea of a tangent line. It's the line that touches the curve at only one point. You guys remember that? So over here, that tangent line is almost horizontal. An almost horizontal line, is that big slope or a small slope?
Small. Slow.
Okay, wait, who's outside? Go open the door.
Hello?
Here, just go outside and see. There's a girl with glasses.
Girl with glasses is gone.
Oh, alright. So, what is the slope of a line that is almost horizontal? It's 0. Right? Now, as I move on, I'm going to move to 1 second later. Let's pretend it's that one right there. The tangent line wouldn't be that. Because the tangent line has to kind of balance on a curve like that. So it would be kind of like this. Right? Is it bigger or smaller? Yes, Justice, I kind of showed you this in class last time. Is it bigger or smaller than what it was before? Before it was almost horizontal. Now it's getting a little bit more angled. Is that bigger or smaller? The angle of this line, the slope of this line.
Bigger.
It's bigger. Is it positive or negative?
Positive.
Okay. So it's bigger and it's positive. You see this? Now, as I go further, is that bigger or smaller? Is this angle bigger or smaller than this angle?
Bigger.
It's bigger. Is it positive? It's positive. There we go. And keep going. Is that angle bigger than this angle?
Yes.
Is it positive?
Yes.
Keep going like that. This is describing, this parabola up here for your distance time graph is describing a constantly changing velocity.
So do you do, and that would be like this here. It's the same thing.
Yeah, it's the same thing. This is the graph you would draw on page 4. It's a constantly changing velocity. You can kind of think of it as what we call the word acceleration. Does that make sense?
Mm-hmm.
And in physical science, you should be learning about acceleration. So that's what it describes. You're taking this and you're figuring out what the velocity time graph looks like. Now, I kid you not that this is actually calculus.
Yeah.
This is the first thing that you guys learn in calculus. So if you guys get this, then hopefully you guys will be home free from calculus. Cool?
Cool.
So the bottom graph, okay, wait, let me read what it says. So the bottom graph represents the top, but in a different form. Exactly, Justice. This is both describing one type of motion. It's describing the motion of something. I think the best story I can think of with this is you're at a stoplight, okay? You're in a car, and you see this Corvette pull up to you, a red Corvette. It's this jerk of a guy. And can you imagine, I mean, the audacity of some dude in a red Corvette revving his engine? Boom, boom. I mean, like, I'd expect to see, like, Barbie next to me in a red Corvette, right? But, I mean, you're a dude. I mean, drive a Mustang at least or something, you know? But anyway, you're inside of your Mustang. They're inside of their Corvette, whatever, okay? And you hit the gas at the green light. You guys both take off. Well, you're not going to start going 100 miles per hour right off the bat.
Your acceleration.
You're going to start to go, you're slowly going to get faster and faster and faster. Actually, if you're in a Mustang, you'll probably get fat, you'll quickly get faster and faster and faster. But it won't be instantly, so actually your velocity will be 0 because you're starting at a stoplight. And then it gets faster and faster and faster and faster and faster. Does that make sense? Now, eventually, your car is going to probably do this. Right? I'm just trying to describe like what it physically would look like. Because now what it's happening is your velocity is getting faster and faster and faster. But there's a problem is it won't always get faster and faster and faster and faster and faster. If that were the case, you could just hold your foot down long enough and then you'll reach the speed of light. I mean, just wait a really long time, right?
Yeah.
So at some point, your velocity is going to top off at its max speed, let's say 200 miles per hour. And if you're driving a Mustang on the street that's going 200 miles per hour, you're about getting like maybe $20,000 worth of tickets right there. But anyway, whatever. You also have kind of an illegal Mustang to begin with, but it's going to top off at some velocity. We call that the max speed. But the beginning of your motion is going to kind of look like that. Does that make sense?
Yes.
All right. I'm going to do one more of these. Let me take a look at what they want you to graph. Okay. Here's what I'm thinking. I'm going to graph this. I'm going to graph the scenario of this. Ready? Throw it straight up. Okay? So I throw something straight up and I catch it. Let's graph that. Why is this pen dying too? All my black pens don't work. You know what? Search in there. Search for me a dark pen inside that drawer. Top one. I need a nice dark pen. Blue doesn't always work. Here, give me that one. No, going closer. The purple one. Here, that one. Let's see if this works better. Can you see that better? Oh, that's kind of a weak sauce one.
Try the blues. Sometimes the blues show up really dark.
You guys see that all right? I can't see that at all. Black seems to be the only one that works. I'm going to go through all my black markers real quick.
There's no black in here.
Yeah, the brown works.
There we go.
Awesome. Okay. So I'm graphing this thing. I'm talking about throwing something straight up in the air. Now I have a question. Wouldn't the graph look like this? If this is my distance? Right? Because it's going straight up. It's only going to go up and then straight down. Wouldn't my graph look like that?
Yeah.
I would say no.
No.
Because,
But it.
but it looks like a parabola. Why does it look like a parabola if I'm talking about throwing it straight vertically up in the air and then having it come straight back down?
Well, it won't come straight.
Well, the answer is this. Because this graph is time. So this is saying as time progresses. Time is always going to progress. So therefore I'm going to get this graph that looks like a parabola. Even though the actual path of it is going straight up and down. Does that make sense? Now this right here is actually describing this motion. Like literally. Like see, look, literally the path that I threw this in is almost exactly that parabola. It's not a half circle. A half circle is more wide like this. No, a parabola is a little bit more pointy than a half circle. Okay? So I have a parabola, and it's a parabola, and its distance is a function of t. And I want to figure out what the velocity time graph looks like. I'm going to actually move to the side a little bit and draw it right directly underneath there. So, here's my question. For the first leg of the trip, while it's going up, is its velocity increase? All right. I want you to kind of tell me. Let's graph this not by looking at the graph, but thinking about really what it's saying here. Okay. Say that I throw this thing up with a velocity of 10 meters per second or something like that, 10 feet per second. Okay. Now, the second it leaves my hand, is it moving with a velocity?
Yes.
Yes, it is. How fast was that?
How fast?
Yeah, how fast was it moving?
I don't know. I wasn't timing it.
I just told you. Say I throw something up
10
with 10
meters
feet
per
per second,
second.
10 meters per second, it doesn't
10
matter.
meters
10,
per second.
10 meters per second. Is it moving the second it leaves my hand? Is it moving?
Yes.
And it has a velocity.
Yes.
Is that velocity positive?
Yeah.
Yeah, 'cause it's going up. Cool. Now, let's say half a second after it leaves my hand. Is it moving up still?
Yes.
Sure. Is it moving faster or slower than before?
Slower.
Why?
Because it's going to be coming down.
Well, because eventually it is going to go down. So we know that it must be slowing down. When I throw something up in the air, it doesn't go like this. Right? It starts off fast and it gets slower and slower and slower and slower and slower and slower and slower.
Until there's
Slower. Until eventually it hits the very top of its motion. At the very top of its motion, what is its velocity?
Negative.
That's not negative. At the very top of its motion.
Oh.
Or here, that would be a good question to ask. Maybe, let's talk about the end of the trip. At the end of the trip, after it's reached the top, is the velocity positive or negative? After it reached the top of its trip, is the velocity going to be positive or negative?
After it reaches the top, it'll be negative.
It's going to be negative. So at the top, all right, I agree with you. It's negative. So I'm telling you that right before it reaches the top, it's positive. Right after it reaches the top, it's negative. If you have something that has to go from the positive side to the negative side, then at some point it has to cross the zero. I say that it crosses the 0 part exactly at the top.
That would make sense.
I'll prove that to you, okay? Give me a second, but let me just finish this. As the time goes on, and we're talking about right after we're going, you're saying it's negative. Before it hits your hand, is it going to be negative? Like, when it's going down and it's up high, is it really negative? Is it the velocity moving really fast? Compare that to the velocity down here. Which one is faster? Down here or up there?
Well, it depends on how hard you throw it, because gravity.
Does it depend? I mean, watch. I wish I could slow down this video. Gross. All right. As this thing moved up, it slowed down. Now, as it was at the top over here, it's going to start to come down. It's moving with the velocity, and then what happens over here?
Speeds up.
It's going faster because gravity is pulling which way?
Down.
Down. And over here?
Faster.
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 Until
Faster. As the time gets, it gets more and more negative, more and more negative, more and more negative. Does that make sense to you? Now let's take a look at this with the idea of that tangent line, okay? Because hopefully I'm going to show you something that will blow your mind. Let's look at the tangent line of this graph right here. This tangent line, is it a big slope or a small slope?
Small. I mean big. Tall.
It's a big slope because it's going very close to vertical. As I get further on that graph, is that a bigger slope or a smaller slope?
Bigger.
Compare this slope to that slope.
Smaller.
It's a smaller slope. As I get closer over here, is that a bigger slope or a smaller slope?
Smaller.
It's a smaller slope. At the very top, if I were to balance this thing on top of this parabola,
That would be flat.
that would be a flat slope, which we all know as
No slope.
0 slope. No slope. Now over here, it starts to go negative. Is it a big one or a small one?
Small.
It's a small negative one. Look right here. Small, negative. And as you get further over here, this becomes bigger negative. Over here, it's big negative. Does that make sense to you? Do you understand how this distance time graph relates to this velocity time graph? Yes, you do? Cool. You understand this, and you'll be stoked on calculus. I kid you not. Now, don't forget this. And by the way, Tejas, you drew your graph wrong. Tejas drew this, by the way.
Oh.
That's wrong. It has to cross the 0 at the same exact moment that reaches its peak.
Oh, I see.
There's a difference, my friends. All right?
Okay.
I'm going to erase. Okay. So let's move on.
There.
Let's cover some other stuff.
Is that better?
Well, you got to keep on going because it keeps falling.
Oh, right.
Huh. All right. Fine. You know what? You guys do this one. You know what? I'll talk about it. We're going back to the same graph there. Okay? Oh, okay. All right. Here we go. So we're saying Tejas is standing on top of a bridge. Here's the bridge. Okay? And you throw a rock up high into the air. So this parabola is going to look kind of like this, right? Right? It's going to start already at some height, say 100 foot or something like that. You're on a 100-foot bridge. It's already starting up at some height h.
Okay.
And it's going to go up and down like that. But it's not going to float in the middle of air, right? So your height is actually going to kind of come down like this. Okay? This is the distance and this is the time. What is the y-intercept? Of this parabola, what is the y-intercept?
100 feet.
100. Very good. It's actually 0, 100, right?
Yeah.
What does that represent in the story? What does 100 represent in the story?
The height of which the rock is thrown.
The height of which the rock is thrown? I disagree with you.
No.
You got to be clearer. What do you mean, the height of which the rock is thrown? I think I agree with you. I'm just kind of confused as to how you said it.
Oh.
Sorry, I speak English in this class. What do you mean exactly?
Where I threw the rock from over the bridge, the height was 100 feet.
The height that the rock started at.
Yeah.
Is that what you're telling me?
Yeah.
Yeah, very good. By the way, I'm talking to Tejas. Tejas is standing right here. If you guys want to come into class, that's fine by me too. But yes, it's the height at which the rock started at. Alright? So that's what the y-intercept represents. Got it? The x-intercept, I'll tell you where it is. It's right here.
That's where it ends, right?
In the context of the story, what does the x-intercept represent? Actually, let me ask you this. What are the coordinates of the x-intercept?
0 feet.
It's going to be number, comma, 0. I don't know what that number is, so I just put number. Right? Whatever that number is.
That would be time.
This would be time. This would represent time. So what does the x-intercept represent then? If that number represents time. Come on, Tyra. I know that you're a beast on this stuff. I want you to jump in. I haven't seen your name pop up in the chat. It means either you're sleeping or you're sleeping. I expect you to sleep. I'm sorry. I mean, I don't think you're lazy or anything. Just saying. You gotta chime in. What does this x-intercept represent? I'll tell you, here's what I'm asking. What does the y-intercept represent? The y-intercept represents how high this rock was when we threw it. What does the x-intercept represent? Say, all right, let's pretend I figured out what that number is. Say it's 4. The x represent is 4, 0. What is that telling me?
That means that after 4 seconds, the rock hit the bottom of the water.
Exactly, Tay. Just say it out loud. Say it with confidence.
Okay. That means that after 4 seconds, the rock hit the bottom of the water.
Exactly. Exactly, Sarah. Exactly, Andre. It's telling you how long the rock took to hit the ground. We good? Alright, good. That was your exit pass. I'm actually doing a lot of this assignment for you. Let's keep going. Let's keep going. What time is it now? I got 10 minutes?
It's 11:03.
Alright, I need to finish at 11:10. I'm going to let you guys figure out this one on your own. Ooh, this one was fun. Alright, here we go. Let's do this one. Actually, this is this one. Okay. Water is poured into a can. Okay? And I have a little floater on that water. So here's the water. It's in the can. Got it? And I put a little fishing bob right here. And what I do is I measure how high that fishing ball is, h, as a function of time. So I want to graph what that might look like. As I pour the water into here, here's my water faucet. Thing right here. So I turn on the water faucet and pour it in the can, fill up the bucket or whatever, and I measure the height of that fishing bob as it goes up, as it floats higher and higher. What would the graph look like? Here, I got a question. Let's just do it all together. Is it? I'm going to fill up this can right here. Is it graph 1, 2, 3, 4, or 5? Keep in mind, I'm filling up. Okay, keep in mind, I'm filling up A, can A. Is it 1, 2, 3, 4, 5? That's my question.
1 or 3.
All right, you think it's 1 or 3? Okay. What makes you think that it's? Why do you think that it's not 5?
Because of the width of the container.
All right. So you're saying that 5 is too slopey.
Yeah. Because I mean, looking at C, the C can, I would think that it fills up faster.
The C can fills up faster because it's skinnier.
Yeah.
And since it's skinnier, there's less water to have to kind of distribute over there, so the thing goes up higher quicker. Right?
Yeah.
Whereas if you have like a medium-sized cup, it would probably be in the middle,
Right.
like that.
So I think 3.
You think it's 3. Why don't you think it's 1?
Because that's too small of a slope.
Right.
That would be more like B, I think.
I agree with you. I think that the answer to part A is number 3. I totally agree with you. All right. Now, that kind of tells us how to do part B and C and D. Let's do this funky one. Say that we have a vase like that. Okay? Actually, you know what I'm going to do is I'm going to switch it up on you. I'm going to turn it, because I was like, what container do I have that looks like this? Say that I want to fill up and wash a salad bowl.
Huh.
All right, I'm going to turn this thing upside down on its head. Can you guys envision this? And fill this up with water, okay? Which graph does that look like?
2.
Tejas says it's 2. Why not 4?
Because it's going to fill up faster over there first.
It's going to fill up faster over where?
The bottom. Because the bottom is slimmer.
Because the bottom is slimmer, it's going to fill up faster. But as it grows, gets higher and higher, the bottom is actually flanging out.
It'll take more time.
So it's going to take more time. So the plunge bob is going to go fast at the beginning, but slow at the end.
The volume is larger at the top.
So it's going to kind of go like that. So I would say the answer is 2. You guys see how that works?
But that's if we had that one. We have the opposite. So wouldn't it?
Yes. If you had the opposite and we turned this thing upside down, the answer would be 4. I agree with you. Because if I turn this upside down, it would fill up the slow part first. It would fill up the slow part, and then it would shoot up faster as it got closer to the top. Have you guys noticed that when you guys fill up? I noticed this whenever I fill up a water bottle or something like that. The water bottle is kind of shaped like this. It's got a little, right? You ever notice that when you fill up a water bottle, it kind of goes at a constant rate, and all of a sudden at the very end it shoots up,
Yeah.
and you want to like get it so it's perfect, but then you're like filling it up, and it goes, whoosh, and you're like, whoa, dude! Like I do that when I fill up a milk jug or something.
Yeah.
Well, that's why. That's exactly what's happening. This graph would look like if I filled up this thing with water, this thing would go constant, and all of a sudden at the very end it would just kind of go like that. Actually, it probably went horizontal. It would just kind of go like that, straight up. So it fills up at a constant rate, and it just goes shoots up straight into that. Does that make sense? That one looks like one of those fan-side water faucets. Oh, okay. Yeah. All right. Yeah, it's water. Oh, this one, the fan-style water faucet. Awesome. Cool. Okay, I'm done with class. I got to go on to my next class, which is physics. So I'll talk to you guys later.